I'll just
We have a few more people here.
all right. So I'm going to be presenting on behalf of Antonio Iovane, who couldn't be here in person. All right. And so a little background on Antonio. He studied electronics in university. He didn't finish his degree because he got a job offer that he couldn't refuse in IT, and he's been working in IT for a long time. And then in 1999, he came across this NASA crowdsourcing type of experiment to study the Allais effect. And he was one of those participants. They accepted him as a participant. He had his instrument there in Italy and everything. And since 1999, so this mysterious Allais effect fascinated him and intrigued him, and he's been studying it for 15 years in most of his spare time. He's built many different devices and done a lot of studying. And after all this time, and most of his passing most of his spare time trying to study the Allais effect, he came to a interesting conclusion, which I'll get to. And so I just want to introduce Antonio because I'm presenting on his behalf, and so we'll proceed from there. So the title of the presentation is "The Lunar Wake as Cause of the Allais Effect." All right, so what I'm going to go through in this presentation, so briefly introduce what the topics that we're going to cover. So the gist of it is it's a possible simple explanation for the Allais effect, and it might upset some people to have such a mundane or unexciting explanation, but basically it boils down to, well, maybe these anomalies are just consequences of geomagnetic storms inducing eddy currents in the measuring devices. All right. So the idea is that the Allais effect anomalies that are measured are actually, should I say, faults in the instrumentation because of induced eddy currents, which is an electrical phenomenon. A varying magnetic field will generate these eddy currents, which will in turn generate their magnetic field to oppose the magnetic field which created them, and so on, and you can have instabilities and so on. So we're going to go over his explanation. We're going to go over we're going to talk about the eddy currents. I'm going to talk about some research he did on the correlations between the geomagnetic storms and anomalies registered by the Torsen, which is a special device which is very, very sensitive. It's a torsion balance, and it's called a Torsen because it's a Torsen indicator rather than a measurement device of quantities, if you will. And then we're going to talk about the lunar wake and the geomagnetic instabilities associated with the lunar wake. Okay. So, first of all, what is the Allais effect? I think most of you here are familiar with it, but I'm just going to go over it real quick. So it's an abnormal precession of the swinging plane of a Foucault-style pendulum, those pendulums that swing like this, and the plane rotates a little bit with time, and which was used, I believe, to prove that the Earth was round, and so to rotating and so on. These Allais effect, the anomalies were found in other instruments apart from the Foucault-style pendulum, such as gravimeters, torsion balances, stationary pendulums, and other swinging pendulums. And particularly, which a lot of the focus of Antonio Iovane's research was centered around a specific device called the Torsen, and a lot of research done by, and based on a lot of data and research gathered by Professor Alexander Pugac, not sure if I pronounced it, of the National Academy of Sciences of Ukraine, using his special torsion balance called the Torsen, which he built himself. So, let's talk a little about the Torsen. So what is the Torsen? It's a very delicate and sensitive balance. It consists of a thin aluminum disc, about 12 centimeters in diameter, weighing 0.1 grams, suspended in the center by a single filament of natural silk. And I think one of the, if I understand correctly, one of the properties of this torsion balance with the silk is that there's very little, you know, when you twist something, it winds up, there's this potential energy which tends to want to bring it back. And this type of balance, it has very little of that. It doesn't tend to wind up and want to
keep running.
Return. It's more of an indicator rather than a measurement. And there's references for all this. I didn't study this for 15 years like Antonio did, so I hope to be faithful to his intended message. It's sealed in a non-vacuum container, so he specified that in his paper. There's air in there. It's electrostatically sealed, but not magnetically shielded. That's the important point there. With an automatic monitoring system of the azimuth of a reference on the disk, you know, so you could know whether it rotated or not. The Torsen data. So a little bit about the data collected by Torsen. So Pugach's data spans a long period of time. It goes from, you know, I think it goes from one solar maxima or minima, a whole solar cycle. It covers different phases of the current solar cycle from minima to maxima. And it shares a common characteristic with many other devices of the same family. Of the same family meaning the devices that have a freedom of movement around a pivot point, such as pendulums, spring mass gravimeters, and torsion balances, whereby positive results are shifted in time relative to the optical eclipse. So a lot of times the optical eclipse will appear at a certain point of time, but this anomaly is registered maybe 1 or 2 hours later. Up to hours is the order of magnitude.
Could you just expand on what the second point is?
It covers different phases of the current solar cycle from minima to maxima.
Yeah, what do you mean?
Oh, what it means is that they've been collecting data with these devices for a long period of time.
But not seeing correlations.
Oh yeah, they're seeing correlations, but we'll get to that.
Okay, good.
I think about 7 years. I think it's about 205 roughly.
2 or 5.
205 roughly. That's like
there's graphs, there's data, so you can see for yourself and make your own conclusions. And if you have questions, his email I can.
I know Antonio.
You know Antonio. Correlations. You're asking about correlations. Okay, so the Torsen activity, correlates grossly on the long term with sunspot activity. And it also correlates with NOAA data on geomagnetic activity and geomagnetic anomalies, and there's correlations. Okay, so it correlates, the activity correlates with the sunspot activity grossly. It correlates with data from NOAA on geomagnetic activity. Antonio found that through his research that he found correlations between geomagnetic activity and solar eclipses and eclipses. And so then the question comes, and this is where his intuition, this is where Antonio's intuition kicked in and said, could this Allais effect just be an artifact of geomagnetic disturbances caused by the Lunar Wake? Right? And so that's what we're going to get into a little bit more deeply. So here, I don't know how well you could see this, but if you don't see it, I'll explain it to you. So on the top, what we have is Torsen activity between the 1st and the 17th of January this year, 2014. So we see in blue is the right. So this is the activity registered by the Torsen. So what is plotted in both cases, the standard deviation computed over a moving window of 60 data points, 1 hour, the blue and the green. So these are variations, what we're seeing, variations. And these computer standard deviations have then been smoothed over 1,000 points moving average, moving window, sorry, the red lines. Right? So these are standard, these are variations, and these are times when there's, there's not much activity. It's not much variation. All right? And this is all data collected from both Pugac and over here. So this is the Torsen activity, and down here in green, this is the magnetometer data from GOES 13 satellite. So we see some, when it's quiet, it's kind of quiet. When there's a lot of, so you can interpret it how you like. So that's just a little comment about the correlations. But we're going to see a lot more graphs with correlations. So the lunar wake, what is the lunar wake? So by lunar wake we mean the eclipsed solar wind. So you have the sun, the solar wind, and you have the moon here, let's say, and then so on the shadow of the moon, right? There's not as much solar wind as in front of it, right? So that's this wake that we're talking about, right? And it's not coaxial with the optical shadow of the moon. It's angled, right, to the Earth, and follows more or less this Parker spiral, right? Like we see on comets and so on. And the wake is also turbulent. It's not a very static. It's not like a shadow, like my hand here. It's still being researched and studied and so on. So, but that's the whole point here, is that it's not exactly, doesn't coincide exactly with the optical lunar eclipse. And so therefore, it could explain the time offset between geomagnetic anomalies and optical, the moment the optical eclipse. And satellite data reveals that geomagnetic disturbances during eclipses, and this is what, through this intuition, Antonio went and researched and found that there was correlation between eclipses and geomagnetic disturbances. All right, so here's one. There's 7. So this is a solar eclipse in Shanghai on July 22nd, 2009. So what we see here is that there's a very irregular, what are the units here? We're seeing, sorry. It's in nanoteslas. So we have nanoteslas here, so we have the intensity. And there's 2 different satellites. There are different longitudes, right? And these represent day and night, right? So, and there are different longitudes, which explains why they're a little bit out of phase, right? Because they're not measuring, they're not at the same point, right? Around the Earth. And then all of a sudden there's the eclipse here. It's quite striking, I find at least, that it's you have this smooth sinusoidal, and then all of a sudden you have, whoops, something happened. Right? It's a pretty interesting variation there. So, Leo Lingchiel had observed abnormal behavior of a ball-borne swinging pendulum on July 22nd. The GOES 11 and GOES 12 satellite magnetometers say that the geomagnetic field was disturbed in the morning of July 22nd. Some persisting noise in the days after. All right?
Something happened 2 days before as well.
Something happened 2 days before as well. Yeah. that's more than a couple hours. On July, August, the sun was spotless. On July. Okay, so you'll notice, I noticed that in his paper he talks a lot about when it's a quiet sun and when it's a noisy sun, to not mix, to not confuse the disturbance caused by the eclipse with that caused by solar storms and so on, which cause disturbances. Here it says on July, August 2009, the sun was spotless. Sunspot number equals 0. Since July 12th and up, July 12th is, that's earlier. And up to August 30th. The July 22nd solar eclipse occurred in a period of very quiet sun. Nevertheless, the satellite magnetometer data for the period of the 17th to the 25th say that in the morning of July 22nd, the solar eclipse day, there was a remarkable magnetic disturbance. I interpret this disturbance as an effect of the lunar wake on the magnetosphere.
Excuse me, the tips after the eclipse, how many hours? About 24 hours or more?
Let's see, here he says, had observed, I don't know over here
I mean, the one you can see where you had it. Just to your wife.
Yeah, this
There
dip,
are
how
some
long,
minimum-
duration of the dip?
Hold on, here,
there are some minimum afterwards.
sorry?
The minima after the eclipse
This
are
one?
after.
Oh, the minimum.
Those.
Oh,
Those
these.
are, how many hours are those?
This
Like
is
the-
24 hours, this is the night and day
So
cycle.
24 hours or 8 hours or 16 hours?
July 22nd, so this is July 22nd, July 23rd. So from here to here is 24 hours.
Okay.
From here to here is 24
Okay,
hours.
no, I'm just saying this because in some of the stuff for the
So from peak to peak is
Yeah.
it's 24
in some
hours.
of the observations by the Turku group in some of
Peak
the
to peak.
there have been some events before 24 hours and after about 24 hours. So it is not a matter of just being next to the
Yes,
optical eclipse, but there are some effects that come about 1 day or 2 days before and after, and they have also been documented by the Turku group in Marabgraph.
yes. So Antonio's explanation for that is well, for one, the measurements of the magnet, the satellites, they may be in different positions, and the Earth rotates, but it doesn't rotate its magnetic field with it, or the magnetosphere stays. The Earth doesn't. The magnetosphere doesn't. You know, it's with respect to the sun, the direction of the sun. So the satellite might be at a different position, and by the time it gets around to measuring it, or maybe it measured it before. So I can read. He put that to me as.
I can ask you.
Yeah. Okay, next one. Solar eclipse over Australia and the Pacific Ocean in the night of November 13th to 14th, 2012. Olinichi et al. Observed anomalies both with torsons and pendulums. The satellite graph of figure 3 shows that the geomagnetic field was disturbed in that night and early morning. So the night and early morning, November 13th, 14th. So geomagnetism in the night between November 13th, 14th. These are still the GOES, this is the GOES 13 and GOES 14 satellites with different longitudes. Just for you to know the difference, one is at 75 west and the other one is at 89 west. In other graphics there were 75 and 136, so there's more of a difference in the phase there of this single that we're observing there. So solar eclipse of November 3rd over Atlantic Ocean in Africa, Pugac detected abnormal behavior of 3 torsons. The satellite data shows a disturbed geomagnetic field in the morning of November 3rd. In the morning of November 3rd. So this is the one that he refers to as
The question.
Yes.
On both the previous graph and this graph, it shows before the drop-off, you have a peak that's higher than previous peaks. But I don't see on there where the eclipse starts, so we can't see
Yes.
how it relates to the eclipse. See, if when we look at the graph, yes, I understand the 24 hours and all that kind of stuff, but where is the eclipse exactly?
Exactly on
But he
here,
does say
yeah.
13 to 14, so it looks like it's going to be close
I
to
think
that.
double
So
dip
is
is
that-
the part of
So
the
the
eclipse.
point is, that higher peak, which is in the previous graph and this, which are both higher than the other ones,
Yes.
right? Does that come prior to where the start of the eclipse, or is that at the beginning of the eclipse? Because there seems to be 2 effects: an effect this way, which is lesser, but it's still left that way, and then an effect to the minimum. So both effects take place, but it doesn't show exactly on there where the eclipse starts.
That's a good point. It would be more. It would be useful to have, let's say, a line or
Shading.
yes, shading.
Yeah, where it becomes more intense at the full eclipse, where it's, you have less of shading at the beginning of the eclipse and after.
I'll make
Make
it.
a shadow there, but it's
Yeah,
pushing
you
it
would have
off
a
the
shadow
side,
so you can
increase
see
it.
what's happening.
Yeah,
Yes.
I'll just take a note of that for
yeah.
for Antonio.
Yeah.
Okay, and by the way, these are all in UTC. So the times are in UTC, so you know, sometimes the time zones might be different. It's not the same time in New Zealand as it is over here. Okay, so let's look at another one. So number 3, solar eclipse of November 3rd, 2013. That's just about a year ago. Over the Atlantic Ocean in Africa, Pugash detected abnormal behavior of 3 Torsens. Is that the same one as before? November 3rd? No, that's 2012, okay. Detected the abnormal behavior of 3 Torsens. The satellite data show a disturbed geomagnetic field in the morning of November 3rd. So, Torsen observation of you know what, I think this is
No.
this is not this. This is the next one. So that's my mistake. Sorry, I prepared these slides. So the solar eclipse, okay. Satellite data showed disturbance. No. So here we have a start and an end. Torsen observation of the solar eclipse. So the solar eclipse starts and ends over here. So we see the what we're looking at here is the Torsen response in degrees and the time, right? So the Torsen is starting to get crazy over here just before the eclipse starts and then drops off back to a steady state later on. And these Torsens earlier, it could be, I don't know if they're positioned in the same part of the world, these Torsens, that might be something to, I presume that the Torsens are not all in the same location, or else wouldn't be much point to it. Okay? And again, Antonio's comments, I interpret the geomagnetic disturbance as a trace of the lunar wake. So, important thing to note that I didn't mention before is that one of the things that got Antonio to thinking about the lunar wake and so on was that during the solar eclipse he found that this Torsen device had activity, but then something strange happened. Was after in between eclipses there was no eclipse going on and it was registering anomalies, and this was during the solar maxima when there was a lot of solar storms. So that's where he started correlating things. And apparently, I think the Torsen. My question would be, well, do we see the Foucault pendulums changing direction when there's a solar geomagnetic disturbance? So I don't know. I'd have to get more details on that. But the Torsen,
They're aluminum? The disc?
it's an aluminum disc.
So it's
Yeah.
not a magnetic effect. Maybe a length of day change?
Because aluminum is not a.
Well, I'm just thinking.
I know it has specific electrical properties. But, aluminum itself. Yes, Bill.
There's an explanation for his Torsen. It's only electrostatically shielded, and so the charged particles coming from the sun or in the magnetosphere that are moving with velocity are not going to be shielded, and so they will register an effect on his Torsen. But he's not expecting that electrical effect. He's expecting it to be due to magnetic fields, but it will be it'll be due to Lenz's law.
Oh, you're saying that even though it's electrostatically shielded, it may not be due to induced eddy currents, but it may be due to charges going traversing the shield.
Yeah, charged fields produced by velocity of charged particles. The particles don't have to.
Oh, right. Yes, I remember that.
Fields will go through.
Somebody mentioned that specific type of field generated by moving particles is not immune to Faraday cages or something along
But
those
see, when
lines.
you have an eclipse, the magnetic field of the Earth, which
Yes.
has a lot of charged particles in it, is
Yes.
disturbed, and some of the particles move faster than normal. And when you have a solar flare, you get the same thing from the sun. The particles coming out are moving faster than normal, and so that's going to produce fields that will get into his torso.
Electric fields, not
Electric.
necessarily magnetic fields, but the electric fields could go through the electrostatically shield. Okay, I got you.
Yeah.
Oh, that's a good point.
But in both cases, there's similar kinds of activity of charged particles.
Yes.
So that might possibly explain some of the things he's seen.
Okay, that's a good point.
And that the magnetic field is pretty large, so even before the moon gets directly overhead to block the sun, you're going to get an effect.
Okay.
And so we were looking at the peaks before the eclipse occurs that were in the readings, and that would be also explainable in this regard.
I took a note of that. Oh, sorry. The last little part there. Also, you said also.
Well, the peaks before the eclipse occurs,
Yes.
they're peaks that we see, and that would also be explained by the same effect because the magnetosphere of the Earth is large, and so as the moon moves to be close overhead, it's going to be disturbing that magnetosphere for quite a distance.
Right.
And so it will produce effects before it's overhead. So
Right.
if you're just looking at the time when you're blocked, you can
Yes.
see that. And my wife and I, we went to a physical eclipse of the sun in Newport News, Virginia, which was in the 1960s. And we noticed that the light fluctuates wildly during the time of the eclipse, and all of nature gets quiet because of these fluctuations.
Were you talking about light, natural light, or light in
Natural light, but that's just due to diffraction. But all these other things are going to be diffracted also and altered in there, and so there's going to be a lot of fluctuations.
If that was the case, then even when you don't get an eclipse at new moon, you should get some effects as well, shouldn't you?
Yes, and in nature you see it. The hunters will tell you the best time to go hunting is at the time when the moon is overhead. And why is that? Because the animals are more active then than on any other day or any other time. So if you want to be able to see them, that's the time to go.
All right. Okay. And what's down here? Okay, so here's the Torsen, and down here is the satellite data for the geomagnetic activity. So there's a correlation, assuming that they're lined up properly. There's lines here, so I'm assuming they're lined up properly, and there's a correlation there. So, number 4, solar eclipse of January 26, 2009. It's an older one. Pugacha and Alamici observed correlated abnormal behavior of Torsen and paraconical pendulum. That's the Foucault pendulum, isn't it? The paraconical? So figure 5 here is the satellite magnetometric trace showing steep variations in the morning of January 26. I interpret them as being caused by the Lunar Wake. So here we have the magnetic, but we don't have the exact time. And so I'll make a point of that. Maybe it's better to have them all lined up so you can see exactly the timing of the instruments, the satellite data, and the optical eclipse. So where's his? I believe it was
The previous day. Morning of the
January 26th. It's that one. A little messed, a bit slightly messy there. And then there was this kind of funny one. I think he mentioned that in his in the full paper. There's a mention also of this, but I don't remember it by heart. You can look at that after if you guys want. It's getting a little late though. We got supper soon. Okay, lunar eclipse of October 8th. Moon at opposition. So this one is a case of when the moon is, you know, if you were on the moon, you would see an Earth eclipse. You know, they call it lunar eclipse. So the sun is here, the Earth is here, and the moon is over there, rather than the moon being between the sun and Earth. And I'm not sure why exactly he put that in there, but I think the reason was that he mentioned there was the instabilities in the geomagnetic field which were caused by normal, well, let me read out. This interesting new, okay. Recently Falaki installed the new Torsen at a different location. He recorded the trace of figure 6. Which shows Torsen activity in the mornings of October 7, 8, and 9. This interesting new test made at a new location with a new device confirms that the Torsen responds to instability of the geomagnetic field. So in this case, it wasn't responding to the lunar wake, it was responding to geomagnetic, and I guess that might be, I don't know why he put that in there, but I suppose it might be in case somebody says, I'm speculating here. I was going to ask him the question, but we didn't have the time. But in case somebody says, well, we registered anomalies when the moon was on the other side. So, not sure. He says here that the bottom of the figure shows the satellite data for the same period. In this case, the Torsen detected ordinary geomagnetic disturbances, stronger in a non-eclipse day, and not the lunar wake, which was on the other side. The eclipse was a coincidence. So he put that in there. I'm not sure why. Okay, solar eclipse, May 31st, 2013. This is a pretty dramatic one. Early morning, Iovane recorded abnormal tilts of a stationary pendulum. Unluckily, he recorded only 8 hours centered on the eclipse, while the geomagnetic field was strongly disturbed since a couple of days, and the effect of the lunar wake is not clearly visible due to the general geomagnetic conditions. Right? Another correlation there. Another eclipse, August 1st, 2008, Gudev et al. Claimed to have observed correlated anomalies on their instruments, but there is no strong evidence of the lunar wake in satellite data. In this case, the satellites I'm using as reference might have not seen all the effects of the lunar wake because their longitudes were too far from the longitudes of the eclipse path. Anyway, the August 1 curve is not completely free of disturbances, and as an example, the blue curve, instead of being quasi-sinusoidal, shows a V-shaped dip. So he just added that, oh, here it is, the V-dip. That's one of the satellites registered the V-dip, the other one didn't. So. Conclusion. So the conclusion is that the Allais effect correlation with the optical solar eclipse has been loose most of the times, and no predictions on its detections have ever been successful based on the optical eclipse geometry. Antonio Iovane suggests that the abnormal behavior of the Allais effect test devices is due to eddy currents induced into the test masses by the geomagnetic disturbances caused by the lunar wake hitting the magnetosphere. That's the presentation. Do you have any questions?